Okay guys, let's have a look at a little intro then for the long click method. We're going to use solving these systems of linear equations then. We should be fairly comfortable at this stage of writing our 2x2 matrix equations, two equations in two unknowns in matrix form. And similarly, the three equations in the three unknowns, we are used to by now writing them in matrix form. Then what we do from there for this method of solving these equations is we form what is termed the augmented matrix. And that consists of the entries from the matrix itself here, and then adjoined by, on the right hand side, by the entries, the numbers there go there. The same pattern follows with the 3x3 case. There's our values, and then we just put these numbers that are here alongside it on the right hand side. These are termed the augmented matrices, the augmented matrix then. And basically, what's our aim? Well, our aim is to be able to manipulate this pattern of numbers, this grid, so that we end up with zeros here, here, and here. So the lower diagonal of these matrices, these 2x2s, that one, and this 3x3, this lower diagonal consists of 0 entries. And then once we've done that, we can simply read off the solution, because if that was 0, then you'd have so many y's is equal to a number, and you could work out y. Once you know y, you'll be able to put it back into the first equation and find out what the value of x is. Similarly here, you'll notice if these were two zeros, then you'll have so many z's is a number. You can work out z. Once you know z, you can put it into this equation, and you'll be able to work out y. And once you know y and z, you can put them both in here, and you'll be able to work out what the x value needs to be. So it's a way of solving these systems of linear equations. So what can we do then to this augmented matrix to enable these entries in the lower diagonal of the matrix to be 0? Well, there's three tools we've got. It's really best explained by examples, but I'll say what the tools are. We can swap any of these two rows without changing the essence of the equations. Yeah, we're not going to change the equations. If we can swap any two rows around. We can multiply a row by a non-zero number, so we can scale up or scale down any particular number just by multiplying it across the entire row. And then the third rule, which is the one we use most often, is we can add or subtract a multiple of any one row to or from a multiple of another. So you might want 3 of these and 4 of this row added together and to go in to replace this row. Or you might want 5 of these, take away 3 of those, and you might want it to go into the second row. So a row can be replaced by a multiple of one row plus another multiple of any other row. Yeah. So as I say, it's best explained by examples, and you'll see exactly what I mean. But bear in mind that these are the 3 rules that we can use. Yeah, 1, 2, and 3. Okay then, guys, little intro there just to get you started, and we're going to start with 2x2s. It goes to a lot of trouble to do augmented matrices, but it illustrates the processes involved and gives us a good little bit of practice before we get into the 3x3 case. The other thing I wanted to say was about what these equations represent, you see, because that's an equation, so many x's, so many y's, and so many z's equals b1, if you think about that. So each of these equations represent a plane in 3D space. That's what they are. So many x's and so many y's and so many z's equals a constant can be pictured as a plane in 3D space. That's what it corresponds to. So you're thinking about this as 3 planes, two-dimensional flat planes in 3D space, and you know that 3 planes will either overlap into a point, and that's when we can find a specific solution, or if you think of 2 planes, for example, say 2 planes overlap and they're one and the same plane, say they're exactly the same plane. If you think of 2 planes, they can cross in a line. So you can have the situation where these 3 equations in 3 unknowns can be shown to be equivalent to 2 equations in 2 unknowns. And if you have 2 planes, they cross in a line. So that's another solution set. And also, if the 3 planes are one and the same plane, they're identical, then the solution set would be the entire plane, wouldn't it? So essentially, you're going to get a point. If there is a solution to find, there will be a point, a line solution, or the entire plane could be a solution to the sets. Most times we're going to deal with singular sets of points being solutions in the practice examples. The other thing to consider, though, that we're not going to address is the fact that when the planes don't meet at all. So you could have like 3 parallel planes, for example, couldn't you? Well, there's no point where they actually touch one another and they all intersect, is there? So you can have that situation as well, yeah? But we're not going to go into the detail of that. We're just going to get used to the processes involved in obtaining solutions. And most often it's just for where 3 planes intersect in a single point. Okay then guys, all the best with the examples. And as I say, they've got an email math button on the mobile app. So any questions, just buzz us an email. If you get stuck on any of the conundrums here, and I'll certainly be happy to, if I get time, to send you a reply. Okay then guys, all the best, and I'll catch you again. Cheers!